Hi, this video is about the dynamics of circular motion. You might remember that there's a distinction between kinematics, which is the description of motion, and dynamics, which has to do with the forces that cause motion. And so Chapter 5 of Young and Freedman's University Physics, which is the textbook I'm somewhat following, deals with the application of Newton's laws. Newton's laws are introduced in Chapter 4, which has to do with various forces, the various aspects of forces. And then Chapter 5 has been dealing with the application of those basic principles to various situations. This is the last kind of substantial section of this chapter, which has to do with forces as they are associated with circular motion. So back in Chapter 3 of the particular textbook I'm using, Chapter 3 dealt with, in part, the kinematics of circular motion, that is, the description of circular motion. There were two equations from that section in Chapter 3 that we're going to start with in this section. So radial acceleration, rad acceleration, radial acceleration is the acceleration toward the center of a circle. If you're swinging a rock around, there is a constant acceleration toward the center of that circle that in Chapter 3 we discovered was equal to the velocity squared divided by the radius of that circle. And if t stands for the period, the amount of seconds for one cycle, then we can use a formula that connects velocity with the amount of distance per time. We can substitute that in to get the second formula on this sheet, namely that radial acceleration is 4 pi squared times the radius divided by that period squared. All of that has to do with describing circular motion. So now, very straightforwardly, because F equals ma, Newton's second law, we can now say that the net force it takes, centripetal force, Young and Freedman strongly discourage even using the word centrifugal force. What we call centrifugal force is not a force. It's simply an expression of Newton's first law. A body in motion wants to stay in motion. And so if something's spinning around and you let go of it, you've not exerted a new force. You've just allowed it to continue on its current trajectory in motion. So we talk about centripetal force, which is the force that is inward, keeping something moving in a circle. And so that net centripetal force is going to be ma, or the mass times the radial acceleration, or since the radial acceleration is v squared over r, it's going to be the mass times v squared over r. Nothing really complicated here. We're simply taking what we learned about acceleration in Chapter 3, and we are now adding the sense of F equals ma to it. Okay? Now, problems in this arena often involve a little trigonometry. So sometimes you have to figure what vector component is that inward acceleration. Let's say, for example, one of the examples in this section is a conical pendulum that spins in a circle. Well, the force is not straight toward the center. You have this wire or whatever that's coming down, and it's spinning like this, and so the inward centripetal force is only a component of the force. It's not straightforward. And so using trig, you know that the cosine of an angle is the adjacent side of the triangle divided by the hypotenuse. And so you can use that dynamic, if you know the angle, to figure out what the adjacent component is, and so forth. So some trig is involved in solving these problems. And then for up and down forces, so if in that conical pendulum you have the force of the weight of whatever it is that's swinging, mg, which is pointing down, but then you also have the tension force of the conical pendulum that's pulling up. And it doesn't go up and down. It stays at the same level, vertical level, And so you have that canceling out of the tension force, or the component of the tension force that's up and down. Again, the sine of an angle is the opposite side divided by the hypotenuse. And so if you know the angle, you can find the vertical component, that's equal and offset to mg, which is the gravity component. So trig is often involved in solving these problems. So a lot of this chapter, a lot of this section are examples, and that's true of this whole chapter. All of this chapter, since it's on application, is example after example after example. So I've mentioned the conical pendulum, where you have something that's spinning and creating a kind of cone with the whatever is holding it, the wire. Also, there is an example in this chapter about a car going around a circular curve, and in order for the car not to spin, then the force relating to friction, the friction force, has to be offset by the force that relates to the circle. That it has to be less than or equal to, or not quite equal to the friction force. Then what if it's banked? What if it's a banked curve? If it's a banked curve, then we can use trig, to basically say that the normal force coming off the bank, if we do trig to figure out, the component that's offsetting the circular, component of the force, if those two equal, then the bank will make it possible for the car to not have to deal with the friction at all. The bank will allow the car to be normal. And of course, this also applies to planes. When planes bank, it's exactly the same situation, except you have some air drag and stuff. But basically, the plane banks to make it possible for it to turn in a circular motion. And then the final example in this section is a Ferris wheel, where at the top of the Ferris wheel you have kind of the normal force pointing down, and then at the bottom you have the normal force pointing up. And so you actually have a larger apparent weight at the bottom of the Ferris wheel than you have at the top of the Ferris wheel. This example is balancing off the mg force and the normal force. So it adds to it at the top and it subtracts from it. It subtracts from it at the top and it adds to it at the bottom. So there's a little flavor of this chapter, of this section of the chapter, which basically applies Newton's laws to circular motion, thus the dynamics of circular motion.